welcome to Lecture 1.5, Robot Intelligence. Intelligence is famously challenging to define, but that won't stop us. So here's the definition. Intelligence is the ability to map perceptions to performant actions. Let's consider this definition specifically with regard to robot intelligence, which is a form of artificial intelligence, or AI. Here, perceptions are measurements. Okay, so we had a map of perceptions to actions. So perceptions are measurements in the robot environment, discussed in Lecture 1.3. Actions are with the robot's environment. The remaining qualifier here is performant, which means to perform well with respect to a metric. Okay, so I think we're all familiar with a metric, something that measures or quantifies some phenomena. Let's consider this last requirement in more detail with reference to Figure 1.7, which let's take a look at that now. We have measurements or perceptions that are provided to the robot action map. Okay, so the robot has some sort of action map that takes in measurements and puts out actions. Okay, that's what we see over here. So if a robot action map did not have a metric for performance, it would offend our sense of the meaning of the term intelligence. For instance, if a vehicle in locomotion perceived an obstacle, was mechanically capable of avoiding a collision, but did not, it would not seem intelligent. If one of its metrics is collision avoidance, it performed poorly and looks dumb, or not intelligent. If it didn't have such a metric in the first place, it looks not even dumb. Stupidly, it was lacking an obvious aspect of locomotion. The term goal or objective is frequently used here, in the sense that for something to be intelligent, it must have one, a goal or an objective. But there is something more implied in the term goal, okay? That is intention. It was the study of biology that first alerted us to the limitations of requiring intelligence to involve intention. Many biological systems exhibit what we would call intelligence, such as the flocking of birds as they fly together, without any sort of coordinated effort. In fact, flocking behavior can be replicated and has been replicated in groups of robots based on simple rules given to each robot. That is, a complex behavior that could be assigned a metric. For example, flocking could be measured by the efficiency of group flying, can emerge without intention. This is called emergence, a topic that is perhaps more mysterious than is necessary. Before we introduce some of the methods of artificial intelligence, it is worth considering some of its applications in robotics. Machine vision systems process image sensor data streams to construct actionable information. This includes object detection and internal model construction. Simultaneous localization of the robot and mapping of its environment, also called SLAM, the acronym, must fuse with sensor fusion, vision, and other sensor data. AI can contribute to this process. Path planning is the process of planning the route the robot should take through an environment. For instance, self-driving cars use map data and GPS to plan its route. Natural language processing can make the robot responsive to human speech and allow it to construct human understandable speech. And now, methods of robot intelligence. The development of AI has been so varied in method that summaries invariably and unjustly minimize entire fields of research. Therefore, instead of attempting a hierarchical organization, we will highlight a few ideas of particular interest. The first is that of symbol manipulation. Here, intelligence is understood as the use of symbolic representations and rules of inference. For instance, if there is a parking spot available on the street, park. Otherwise, circle the block. There are several symbols here. For example, a parking spot, the street, parking, block, and circling. This approach has encountered formidable challenges, such as the signal-to-symbol problem of going from measurement signals to appropriate symbolic representations. In the example, it is challenging to determine from sensor measurements what is a parking spot. This approach also encounters the vast ambiguities in natural language. Consider the multiple potential meanings of the sentence, "There's a spot." Natural language processing is now an entire field of AI. Logical approaches to AI understand intelligence to be comprised of reasoning. Reasoning requires a knowledge base with semantic, i.e. meaningful, relations. So, knowledge representations have been a significant aspect of this work. This approach features, for instance, the ability to make plans. In reality, nothing is certain, so logical methods have come to use probabilistic reasoning with, for instance, Bayesian networks. Another type of reasoning is called fuzzy logic that is used in this type of reasoning system. Beyond the minimum requirement set forth in our definition of intelligence, it is certainly a mark of intelligence to adapt or learn. In other words, to increase intelligence from experience. So, consider again the vehicle in locomotion and perceiving an obstacle it is mechanically capable of avoiding, now illustrated in figure 1.8. So here we go. We've got our robot hurtling toward an obstacle here. If it has as a metric to avoid obstacles, it might still hit the obstacle if its action map is insufficiently intelligent. Now consider if this map is trained on many obstacles, such that it tweaks the map in accordance with its obstacle avoidance metric. This would yield an action map, the performance of which improves in intelligence. Taken broadly, this program is called machine learning, a leading strategy for developing artificial intelligence. One method of machine learning uses large amounts of data to make inferences about what should be done, making it inherently statistical. A simple example here is the technique of regression, fitting a function to data by optimizing the function's parameters. We've all seen regression used in maybe physics lab or an engineering lab, where you've had data points that lie maybe close to a line, okay? And then we have come up with a linear regression or a function that describes approximately the shape of those points. Okay, that is regression analysis. So in a line, we have y equals mx plus b. We have two parameters, the slope and the y offset, that we can tweak to better fit the data. So those parameters would be optimized to fit the data, using, for instance, least mean square distance to the line of these data points. So that's an example of linear regression, and similar methods can be used for more complicated functions than just linear functions. Another machine learning approach is to train an artificial neural network, a mathematical operation that approximates the function of biological neural networks that are key to brain activity. Typically, a set of training data that includes labels, which are the correct answers, usually assigned by humans, is processed by the network, which adapts its parameters such that its output approaches the correct answers. Then, labeled testing data, so data that comes along with answers as well, on which the network has not trained, tests to see how well the network performs on new data. Relatively recently, a combination of advances in computing power and new approaches to using neural networks has been highly successful, surpassing previous performance metrics for many important applications, like ones we've seen: vision, natural language processing, game playing, etc. So things that are relevant to robotics. The new techniques use multiple network layers and are collectively called deep learning. And the deep comes from the number of layers, depth of layers. And now we can discuss control theory, one of my personal faves. A control system, which control theory studies, is comprised of a system to be controlled called the plant, a feedback measurement of the plant's output, and a controller that determines the plant's input, given the feedback and some goal output. This is frequently represented in the block diagram below. So this block diagram has a plant. So this might be, for instance, a robot link with a motor in it. And the output of that might be the angular position of that link. We measure what that link position actually is, perhaps with an encoder, and we give that measurement to the controller. The controller then compares that to what the command is, which is where we would like that link to be located, and decides what control effort, which is perhaps maybe the voltage, the electrical power that's going to be applied to the motor, that will turn this robot arm link to be closer to or equal to the command. Okay, so this is a standard sort of feedback control systems scheme of doing control. If it is successful at meeting performance goals, such a system meets all the requirements of artificial intelligence in our definition. Although control theory developed as a separate field from AI and precedes it in some ways, it is in fact another form and is now generally recognized as such. Control systems appear all over most robots as subsystems. For instance, a robot arm joint usually includes a motor, actuator, an encoder, sensor, and a controller. The plant then might be the motor link assembly, like we just thought about. A process in some higher level controller that perhaps has planned the arm's motion and performed an inverse kinematics calculation would send a command to the joint to rotate to a specific angle. General artificial intelligence. There may be objections at this point about our threshold for intelligence being too low. Some find it to be so because they conceive of intelligence as being what is now called general artificial intelligence, a single AI system applicable to any problem. For instance, it would be capable of navigating a robot, having a conversation, and playing the cello. This is sometimes called strong AI, in contrast with the version considered above, now termed weak AI. There is no strong AI yet. However, if it does emerge, it is possible that it will develop beyond human intelligence rather quickly, into a state called superintelligence. There are ethical concerns here, with some potential for superintelligence becoming an existential threat to the human species. So it's worth considering this. It's one of those Pandora's box problems where once we open it, we can't close it again. So it's worth making sure we understand what we're doing with this regard, which as humans, we don't have a good track record for that so far, but I'm hoping we improve. We need to. So, yeah, that is robot intelligence. There's obviously a lot of stuff packed in there, and later in the course, we'll unpack some of that. All right, take care.